only. Whose area?
And then this office, it appears to be quite big. That hall where
Yes,
you are.
yes, 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 yes.
So you are alone here?
Yes, I am alone. This is the
Oh,
place where I attend interviews and all.
okay. So then I am being interviewed.
Yes.
Okay. So good evening to all of you who are doing this course on NPTEL on Introduction to Launch Vehicle Analysis and Design. I am Ashok Joshi, the instructor of the course, and I am happy to be interacting with all of you in this session where you can post your queries and to the best of our abilities we'll answer. There are two TAs who also joined, Dr. Karthik KN and Dr. Girija. They are TAs. And from NPTEL side, Mr. Sandeep Lavate is there. So let me just give a brief overview of the course that you are going through. The course is essentially in the area of launch vehicle trajectory and vehicle configuration design. That's the primary objective of this course. And the various topics and the videos that you would have seen are essentially in the context of generating a launch vehicle trajectory and creating its configuration from primarily a design perspective. In the context, let me mention that the design perspective comes from the fact of what is the desired terminal performance. Even though you might have noticed in some of the lectures, we are going the problem in the forward manner that we have a configuration and we want to calculate the terminal performance using our basic trajectory analysis. In reality, it happens in the reverse direction, that you are given a desired terminal performance and then you come up with two quantities, that is what is the trajectory that should be taken and what is the configuration of the vehicle which will achieve this trajectory so that the desired terminal parameters are achieved. So this is how the overall launch vehicle configuration design along with the trajectory is practiced in most of the space research organizations. This is typically a coupled problem where the configuration design and the trajectory design are done together. In the present case, in order to understand this better, we have kind of split the two. We first look at the forward problem of how to generate a trajectory given a configuration. And then, of course, we move over to the second part, that is the configuration design, where you specify a terminal performance and see what is kind of configuration that you can get. So I hope you have a reasonable understanding of this from the various videos and the slides that have been made available. And I'm sure you would have some queries on. I understand that a couple of queries have been posted. So one of the queries which I thought let me address straight away to the participant who posted that query. I don't remember the name. Karthik, can you tell me the name of the person who?
So the drag part.
Yeah, that the direct part.
Yeah, a participant named Pooja.
Pooja. So is Pooja connected? Uh, okay, so this is some Pratik Kumar Jaina who has joined. At least I see. Anyway, I presume that even though Pooja has raised this query, there might be others who might have similar lack of clarity with regard to the. Good evening, Pratik. How are you? Welcome to this session. So, let me just give you an overall perspective on what exactly is the issue of drag in the context of launch vehicle trajectory design. Before I focus on the specific question which has been raised, let me first give you an overall idea of why are we talking about the drag. What you need to realize is that, strictly speaking, Okay, this is your first class, right? Good. Yes. So let me just give you an overall perspective. Drag is essentially a nuisance as far as the trajectory is concerned. This is the first thing that all of us must realize. Strictly speaking, if the drag was not there, we would be happier. Only thing is that we cannot wish away the atmosphere, particularly as we lift off from the ground. So obviously, we have to deal with drag. As we try to avoid all other aerodynamic forces while performing the ascent mission, but we cannot really get rid of drag completely. And drag can create a problem in terms of overall efficiency of the performance. And in order to optimize the vehicle and in order to get the best out of a given launch vehicle design, it is important for us to understand the implication of drag. So the model which I created in the uh, lecture that I thought I will share with you just to give you some idea was that, can you get a overall estimate of what the drag will do to you in a given mission? So it's essentially a gross estimate, a bit of an approximate representation of the actual physical effect, but it gives you an initial idea in the conceptual design of the vehicle as to how much energy you are going to lose to drag. And if you don't want that energy to be lost, then you can compensate it by providing additional energy in the configuration design, which means it will directly have an impact on your configuration design in terms of the propellant that you will be required to carry, or the amount of payload that you could carry because of the loss of drag, loss due to drag. So all those issues you can resolve. Let me see if I can just share the screen. I'll present my entire screen, share, and yeah. So I will start with this particular picture, which I think at least Karthikeyan was telling me that this was what was commented on. And this is the fundamental, what do you call, basis behind the analysis of drag that we have done in the present lecture series. What we are trying to do here is to estimate the total amount of energy that is going to get lost because of the drag. And this particular plot is such that it can be interpreted in the form of an energy which comes as area under the curve, because this is altitude versus drag force. So it is force versus altitude, right? And if I do the integration of this, the area under the curve is nothing but integration. And that integration is nothing but drag into altitude, which is energy. Force into distance is energy. So this is the fundamental idea. So what we do is that we try to find out what is the extent of energy that is contained in this plot. Now this energy is actually a loss because drag is in the direction opposite to your motion. So obviously this will represent a loss. The idea essentially is that if I can create a loss model, so what you see in this red line, which in form of a triangle, is a kind of a loss model that we have proposed so that our analysis becomes simplified. What we are trying to do is we are trying to ultimately get an equation with constant coefficients, as I wanted to show you here. Yeah. So this is the constant term, which means I am replacing the total loss of drag energy in the form of a drag deceleration. So this term is a basic term which now controls the whole trajectory. That this is the effective drag deceleration that the vehicle will experience because of atmospheric effect. And then of course, as I've given problem, and I'm sure in the video that I've posted, you would have seen this example being solved. So here what we are trying to do is that we are trying to take a baseline solution. The baseline solution is essentially where there is no drag but there is gravity and a straight line vertical motion. So this is the baseline configuration of trajectory that we are looking at. And then we are saying that over and above this baseline configuration, if there was an atmosphere present, based on that drag deceleration model, what would be the loss in the performance? And this is precisely how we have done it. So what we do is, in a very simplistic manner, we come up with the basic trajectory performance in terms of velocity and altitude profiles. And then we say that at a particular altitude, the drag would be maximum. And this is in relation to this point. This is where you would get a peak drag. And then we say that the maximum drag value is what I'm going to use as a kind of a benchmark for this model that I have created for energy loss. And based on that model, what we do is we then project that if this was the baseline trajectory, which represents a particular dynamic pressure value, then at the peak dynamic pressure, I'm going to calculate the drag value and say this is my maximum drag deceleration which is going to be experienced by the vehicle. Once I come up with the term maximum drag deceleration, I simply use a rectangular approximation of the triangle to say that this is the average drag deceleration that I can use in my equation which I showed you. And that's the strategy that has been used to show in the present case. Of course, certain other simplifications we have introduced to say that the altitude at 50 seconds is where the peak occurs. In reality, it is not going to be as straightforward. It's then going to be a non-linear iterative process where you will have to go through this cycle multiple times to arrive at the solution correctly. But I'm just showing you the first step in this idea. The first step is that locate the peak drag force, divide by the mass at that location because it's a mass depletion scenario, and you get a maximum deceleration. And from maximum deceleration, you arrive at average deceleration. So this is the maximum at that altitude. And then half of that is nothing but your average, which is over the trajectory altitude. So you just use this in your baseline trajectory equation and recalculate that if this was the effective loss because of drag, what would be the loss in the performance? And as you can see, there is a loss in performance in terms of velocity as well as in terms of the altitude. Now, of course, this is only a broad approximate estimate, but it still tells you that by doing this, you can arrive at a reasonable idea of how much to account for loss due to drag. There is a connected example of a higher burn rate just to give you an implication of what is the impact of configuration of launch vehicle on the trajectory. Configuration is in the form of a burn profile or burn rate. And in this case, you can see that the impact is a lot more significant on the velocity as well as on the altitude. And this is what the launch vehicle trajectory design and optimization is primarily all about: how to manage this loss and to manage this loss such that you get as best performance at the end of the trajectory as possible, and that will directly have an impact, as you can see, on your burn profile. And this burn profile will now go into your configuration design of your rocket motors. So you will find that this is where the trajectory and the configuration design connection is. I hope the point has been adequately understood. If there are any other issues that any of you would like to raise, you can put it in the chat box. We will look at it. But otherwise, we will take other questions which are also raised by some of the participants.
Sir, I'd
Uh-huh.
like to add some point.
Okay.
So this drag profile which we have chosen,
Uh,
like, so in reality we have the drag coefficient as a function of angle of attack, Mach number.
correct.
So instead of doing that elaborate
Well,
modeling,
uh-huh. No, no, you
so
can
we
do that.
have
You
tried to
can go.
uh,
No, I understand
in
your question.
in this example, in
Uh-huh.
this example which the way we are doing
Uh-huh.
is, instead of doing that way, like we have
Mhm.
a graph of CD versus alpha, and
Correct.
so we have tried to find the average drag effect
Correct.
which will happen throughout our profile,
Uh-huh. I'll tell you
and
the
we try
reason why.
to
Also tell you the reason why we have done that.
yeah,
See, when we talk about launch vehicle trajectories, all of us know that it is going to start from rest. So zero Mach number condition, it will cross
right,
the transonic Mach number. It will go to supersonic Mach numbers close to
right,
2.53. The problem
mm,
is that this most of the launch vehicles you will find that they have a blunt nose,
yes,
because the blunt nose, typically you will get a normal shock condition in
okay,
uh, uh, at the tip of the launch vehicle. Now
like a normal shock,
behind the normal shock, the flow is generally subsonic. So
okay,
no matter what the free stream Mach number is,
okay,
the Mach number behind the shock is likely to be
subsonic,
subsonic.
mm,
And typically for subsonic, the CD values are some kind of a ballpark figure that we have chosen in the present context. So that is one aspect of this whole process. The
okay,
second aspect of this process is that the frontal area which is exposed to the air is constant. So the drag coefficient per se does not change because of geometry. See, the drag coefficient will change because of two things. One, because of geometry, and because of Mach number.
mm,
So we kind of get a situation where CD is more or less constant throughout the flight.
okay,
So that is
mm,
why our whole of drag profile is driven primarily by altitude and velocity in
okay,
terms of the dynamic pressure. That is why
mm,
typically in most of the launch vehicle design, dynamic
mm,
pressure becomes the fundamental parameter from the aerodynamic perspective.
okay,
So what you saw in this picture that I showed you is essentially the dynamic pressure profile,
mm,
and dynamic pressure multiplied by a constant CD and a constant frontal area is a
mm,
directly can give you a scaled version of the drag force itself.
yes,
Yeah, Pratik, you can leave, no problem. Yeah.
okay,
So this is what this drag based analysis is all about. I mean, I'm
okay,
presuming that the participant who raised this question
mm.
is now
So
at least
so
clearer about what is going on.
okay. So in assignment 3, question 10,
Uh-huh.
so it was not specified clearly that the peak deceleration occurs at what altitude.
Uh-huh.
So so in our solution, we
Mhm.
had used that the peak deceleration occurs at 10 kilometer
Mhm.
based on the graph which you just showed.
Correct.
So
So,
people found
okay, so
difficulty.
let me tell
Yeah.
you also that in case uh, this information, see, what you need to realize is that this information where the actual peak will occur will you will get only after solving the problem. It's a nonlinear problem. So
Okay.
upfront, you will not have a very clear-cut idea of where the peak will occur
Mm.
unless somebody gives you externally. When you are doing the design, information is not available to you for your configuration. So what you do is that you use those plots which I have shown you as a kind of a starting solution. You can assume that around 10-kilometer altitude, the peak is likely to occur. Make that assumption. Based on that assumption, you generate your solution, and then you look at the solution as to whether it is really around that or not. So you may need to do a little bit of adjustment in the real design scenario, but in the present context, if you have assumed that it is at 10 kilometer, it's perfectly fine. Your baseline solution without the aerodynamic or without the drag effect will automatically give you a velocity profile at this altitude. So you can say that, okay, what is the velocity or how long will it take to reach this altitude? And from there, you can find out what is the velocity. And once you have the velocity and altitude with the density, you can get the drag value. I hope that addresses the point that was raised in assignment 3 or no? Is there something residual left?
Yeah, sir. I think people would have got a better understanding of that, how to do the
Okay,
drag.
correct.
Hmm.
Okay. So are
Yeah.
there any other points which have come in the chat box now? Or whatever
Uh,
was posted?
like in the chat box, no questions have come yet. So we
Uh-huh.
will go with the second question in the form itself.
Okay, no problem.
Uh, yeah, so that is from assignment 4, question number
Uh-huh.
9.
Uh-huh.
So, so in that, like I think the student wants a little bit of overall briefing of what has to be done. So I can share the screen so that
Go
you
ahead.
can read the question.
Yeah.
Yeah.
Okay. So if you share the screen, I will read the question and then maybe I will respond
You
appropriately.
can. Yeah, because assignment 4 solution got uploaded just a few minutes before, so they
Okay.
might have
Okay.
not
Ha,
observed
ha,
it.
ha. So this is the question, right?
Yes.
Uh-huh. Okay. So let me explain the philosophy of this question.
Yeah.
Now, this question essentially is talking about the curvilinear motion, which is an essential aspect of any trajectory design. But what happens is that you cannot start the curvilinear motion in the vertical attitude. That because that represents a singularity in the curvilinear solution equations. The vertical attitude, that is theta not equal to zero condition, represents a singularity. That one can always see from the point of, if you look at the equations which are written down for this, participants and students can look at those equations. The problem is that you still need a curvilinear trajectory, but you can't start. Now, let me just take a slight digression. In the olden times, when there were no control systems in place, for example, in the late 60s, when this whole sounding rocket program started, and we were also part of that, that time, the rocket had no intelligence. It was just a kind of a shell with propellant inside. So, and once you ignite, it will simply fly off. So what they would do is that they would create a kind of a launcher on which the sounding rocket will be kept, and that launcher would be given a small angle from the vertical right at the beginning, so that right from the start it will move on a curvilinear trajectory, and the launcher for some time will constrain its pitch down maneuver because it was a rigid structure. Now, of course, we have come a long ways from that point of view, and we actually have all these launch towers which many of the participants or students would have seen, where you are keeping the rocket perfectly vertical because it's a huge structure. A little bit of tilt from the vertical will generate a huge amount of bending moment on various sections, that there is a danger that it could have a structural issue right at the launch pad itself. So you can't afford to have a tilt. So in order to now have a curvilinear trajectory, but still starting from a vertical attitude, this pitch over maneuver is what is mentioned here. So this is a reflection of that kind of a scenario, that you lift off vertically and within no time you take a pitch over maneuver, which means your curvilinear trajectory will start from a non-zero theta naught and a non-zero velocity. It cannot start from a zero velocity and a zero angle. So this is the fundamental principle for working out this problem. So that initial 10 seconds is where you have given the vertical motion so that it acquires a velocity, and once it reaches that particular velocity, you give an impulse which is only in angle. So it's an angular impulse. That is the pitch over maneuver or a pitch kick. And instantaneously, the theta from vertical becomes non-zero, a slight small amount. And then from that point onwards, the gravity turn solution will take over to generate the curvilinear trajectory. So I hope this philosophy of solving this problem is clear now.
Okay, I'll just. Uh, so the participant says that she has understood the drag-related problem. Uh,
Okay, good.
so let's
See if we
see.
get any reply for this part also.
Yes. So since we have
Meanwhile, we
not
can take
got.
the other question. Meanwhile, we can take the other question if there is any.
Yes, I think the technical questions are
Over.
over.
We can also take
So
non-technical questions. Non-technical questions.
yes, there are a few questions related to the exam pattern.
Haha. So that I think you can
So
reply better. I think, right, Karthik, and you know the exam pattern, and probably Sandeep should tell us how much we should be telling at this point. So Sandeep, what is your take on it? Haha. Yeah. I mean, I don't think we can give out too much information, right? Yeah. So, I mean, what we can say is that, Sandeep, can we say that it is kind of a online exam or something like that? Online multiple choice questions. They could be linked questions, and then they will require some amount of working out independently, numerical answers, all those things we can say, right? Okay, okay. So Karthik, I think now you know what to mention in the reply to that. Yes.
okay, so that we will post it
Then
so
I
that
think it's better. Yeah,
everybody gets to
because that query could be for many other students.
correct,
Just because one
correct,
has this doesn't mean the others may not have a similar doubt. So I think we can
right,
simply paste it to the
right,
as a kind of reply to that question. But
correct.
finally, now you
Because
know what not to say.
yes,
Yes.
yes.
So just one more thing.
Yeah. Yeah.
Some people are, while doing the problems, some
Uh-huh.
people are just confused what the unit of degree they have to take, whether it is
Yeah.
radians or whether it is degrees. They're very confused about that. Uh,
Mhm.
the Q0 value. First we
Q0 is
get
it?
to
See, Q0, see, if you see equations, see, please understand this. The way we have written the equations, they do not recognize degrees.
Mm,
But that is not to say that you cannot use degrees. If you can always write that equation, rewrite the equation, assuming that your Q naught is in degree units. So automatically 57.3, which is the conversion factor between degree and radian, will appear in the equation.
mm,
That's the only difference that will happen. So it is not that students cannot work with degrees per second or radians per second. The way we have written the equations, we have not taken the degrees into account, because when you take sine of a degree, that also is equivalent to a radian only. It doesn't come back in degrees. So the equations are all radian compatible. So that's why your Q naught, which is your pitch rate, would be radians per second, not degrees per second. The way we have written the equations, which means all the lectures where they have written. But it is very easy to bring in that factor of 57.29, and the same equation can also be used in degree, which means your pitch rate can be used in degrees per second. Does not matter.
mm.
But you must be consistent in your degrees. That is the only point. The currently the way equations are, they are consistent with radian per second. So, Girija, I hope that will kind of address the issue that some people might
Yes,
have.
I think so. I think so.
Yeah.
So, sir, there is one question in the chat box.
Tell me. You can
Uh,
read
s-
it. Tell me.
yeah, it's from Pramath.
Uh-huh.
He asks, sir, how do we use the reference books to solve more problems and to understand concepts better?
Uh-huh. See, I have mentioned, I think, some three or four books. I would say that the Hale book, Hale, I think there is an author. I remember I putting that book, as well as Weisel. Weisel also is reasonably okay. So there are problems which are given at the back of the various chapters. So you can try those examples. But only thing is that most, at least Hale has some solved examples where you can verify your result. But if they are unsolved examples, then you will have to probably check with TAs whether if you have solved a problem and you want to find out whether what answer you have got is correct or not. I think they may have mentioned the answers. I don't remember, at least in the Hale book. But otherwise, I'm not sure whether the answers would be available in the unsolved problems. So, I mean, one can only say that if you are using a consistent approach, then possibly you would be getting the right answer. But then that is something that you may have to check yourself, because sometimes what happens is that the answer, by looking at the numbers, you get a feeling that this cannot be the answer. That maybe it cannot be this large or this small. Maybe so. Basically, you need to develop some kind of an expectation of what should be the answer. There can be certain sometime a simplified approach or two alternate approaches just to see whether the number that you are getting are okay or not. But otherwise, there are no what do you call shortcuts to the answer. You will have to go through the hard work. I hope that point is addressed. If you can ask him if he's or whether he wants or he had something else in mind, and we have not addressed that question.
Let's wait for his reply.
Yeah.
So, until that, we'll take the next question.
Yeah. Okay.
So, it is from Shubham. This is a
Project. Now,
yeah.
let me first of all, it's an only an 8 weeks course.
Mm.
Now, in an 8 week course, I'm not sure, probably Sandeep can tell us whether there is a room for maneuver in terms of where students can do a project. Now, the other aspect which is there, how does one uh, provide credit to the project? Because there they have a standard format for evaluation where they have assignments and the final exam. So whether in that format a project can fit in that in place of some assignments, because they want one assignment every week. But in case of a design activity, it may not happen like that. So to some extent, this question goes back to NPTEL and Sandeep, where this issue can be addressed better. I have no objection in giving a small project of designing a launch vehicle trajectory by giving a requirement and saying that can you come up with the configuration of launch vehicle as to what kind of see, some of the assignment problems do have that design perspective,
True.
but then they are in a very limited context. So I think to that's I think probably NPTEL is in a better position to answer that if such a thing is possible. From our side, we can definitely include some design exercises. There's no difficulty. The second part of the question about having real launch vehicle design
On existing launch vehicle analysis,
vehicle.
must
Now,
include this
that
conversation.
I would like to answer in the following manner. The real launch vehicle or existing launch vehicle design is an extremely complex and involved exercise, which also talks about things like operational issues and various other trajectory management issues which are not part of the present course syllabus. So, and to practice that as part of this 8 week course is not really going to do justice to the exercise, because if you really want to do a real life existing, for example, suppose you take something like PSLV and say, can we do the PSLV design? The PSLV itself was designed by ISRO over a period of 12 years. And to be able to capture even the highlights of that in an exercise, at least to me, it doesn't appear to be a feasible option. What possibly we can do, which I will take feedback from this to say that uh, as part of the multi-stage design, and when we are talking about the configuration design of launch vehicle, we have mentioned some uh, realistic vehicle configurations that, for example, for PSLV, we have talked about what kind of stage of structural ratios, the propellant loading ratios, the ISPs are there. So we could talk about those for a large number and make a comparison of different kind of launches in relation to the mission that they are being used for, and to give you a better perspective of the overall configuration process. But I'm not sure that the actual existing vehicle design per se would fit into this whole game. I mean, at least in the 8 weeks I don't see a possibility, because until you get the basics in the place, it
Mhm.
will be difficult to appreciate. And by the time 8 weeks are over already. Yeah. I mean, that's all what I
Yeah.
thought I can mention at this stage.
Yeah, so I would like to add to this.
Uh-huh.
So for the viewers, in Sir's course at IIT Bombay, so he actually offers us to like a assignment where we take where every individual is assigned a different real life actual launch vehicle, and we are supposed to do from end to end complete analysis. So like this
Yeah.
happens
But then that
in a
exercise, that I mean, generally, I give 1 month for people to actually complete that
right,
exercise. And this whole
right,
course is over just about 8 weeks.
right.
But
So.
in that, I mean, it is a basically kind of 16 weeks course. So basically double the size of the present course.
Mhm.
And then they do end-to-end mission analysis, and then come up with the configuration, the trajectory, and then try to
Mhm.
match with the actual trajectory and the actual mission of that particular launch
Right,
vehicle and the satellite.
right,
So basically, it's a launch vehicle satellite combined that we look at as a mission.
right.
Yeah.
Yeah.
So
So I think we'll
is there anything else that we would be doing that?
yeah. So there is one more offline question.
Okay, go ahead.
So this is from Mr. Sampad.
Mhm.
Uh, he's been very active in the forums actually,
Mhm. Okay.
and he actually replies to all the queries from other participants much faster
Okay.
before we discussing and
Okay. Okay. I understand. I
make
understand. Which
so
means he's on our side.
yeah, he's on us. I think
So
we
you
should
can pass on
include.
this message to Mr. Sampath if he's listening. That yes,
I think we should take
we
him
are
as a
appreciative
TA.
of your help. Yes.
So his question is,
Mhm.
I'm currently enrolled in this course and I'm aspiring for a career change to ISRO DRDO.
Mhm.
Currently, I have 17 years of IT industry experience. I've been
Okay.
very good with the assessment so far, and I'm confident to clear the final exam with a good score.
Uh-huh.
I'm very passionate about physics. Can I be provided an opportunity to serve my country?
That I mean, I think it's not my place to answer whether ISRO would be looking at whatever you have done as part of this NPTEL course and give some credit to it, and uh, 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 be interested in you to be part of that organization in launch vehicle analysis, design, and similar things. But my another take is that if you are really passionate about these kind of things, maybe you can start thinking in terms of small space related activities, which with this basic understanding you yourself can initiate, maybe in the form of a startup or in the form of some kind of a small activity. And once that catches on, maybe there would be a possibility of some private enterprise or sub company which might be, because space essentially still is in the government sector at the moment, even though ISRO has been having it's what you call a commercial arm where they do talk about commercializing, but that is mainly from the launch slot and the what you call selling the satellite time, launch time for the launch vehicles and those kind of things. In fact, now they are talking about a small satellite launch vehicle development which they are recently doing. So I'm sure that is where I think Sampath would find a little bit which he can contribute. So maybe what you can do is to get in touch with people who are doing similar kind of things. Maybe create a kind of discussion group who feel similarly about the space related activities. And there are many universities, colleges where they are talking about small satellites which they are making, and then they want to then launch them for various low earth applications. So there are immense opportunities and possibilities. But whether ISRO would directly be involved, I mean, it's not my place to say. So I will probably keep out of that part. I mean, but I'm just giving you a perspective on what possibly one can look at in the present context. I hope I have addressed to some extent. I know that it is not fully addressed, but this probably is the best that I can do in the present context.
Yeah. I can also add a little
Yeah,
bit.
please go ahead, Karthikeyan.
Yeah. So, like, apart from ISRO and DRDO, like Sir said, like there are a lot of startups who have already started testing a lot of stages, like not actual flight tests, but ground testing and all. One best example is called Agnikul Cosmos,
Mhm.
and they are also doing very good. And I think the current government's perspective is also to give it to private companies rather than
Yeah, yeah, that's right. That's right.
so ISRO DRDO will be doing the most niche technology pushes
And
and
rest they
all
will
the things.
simply kind of offload to
Yes,
the private players, the startups, and all that. So there
right.
is a likely to be the next 5 to 10 years a huge market for these kind of things
Yes,
from private players, and
yeah.
that where probably where the I think he can get into.
So yeah, so Mr. Sampad, like ISRO scientists, they themselves are getting out of ISRO and starting
Yes,
their own startup.
correct.
So that is that's the type. I
Yes,
mean, it's yeah.
I think currently we are seeing the emergence and evolution of the startup culture in India, which I think happened in US probably 30, 40 years ago.
Hmm.
That is when the Silicon Valley, a lot of startups came. But now, I think last five
So,
to 10 years, we are also looking at the whole idea of startups, and then they are also becoming quite active in this field. So as
hmm.
you are saying, Karthikeyan, I think this is where probably Mr. Sampath should be kind of focusing on. I hope he's reasonably satisfied with our response.
Yeah. So Mr. Sampad has one more question.
Tell
Uh,
me.
so for it's from the chat box.
Mhm.
So for human spaceflight, are we planning GSLV Mark III or a variant of it? For that variant, are we changing propellant or structural details or ISP?
That is a question which is a kind of an intellectual property of ISRO and only they can answer. But
Hmm.
from my understanding of space, when we talk about human space flight, as against, let's say, a normal, I mean, if you just were to compare, let's say, GSLV Mark III, which is launching a satellite, and GSLV Mark III, which is taking humans, the basic difference would come in terms of the reliability that you would like for the vehicle and the mission. See, this is where the major challenge comes in the design, that whenever there are humans involved, the level of reliability has to go sufficiently high so that the risks are practically not there. Now, what that would mean in terms of the structural design or propellant configuration or ISP is an entirely a study by itself, and it is probably in the purview of the ISRO to work this out, because this is essentially a reliability related. See, PSLV by itself has proved itself to be a fairly reliable vehicle. But when you talk about human mission, there are additional requirements which come onto the vehicle, which will obviously indicate of different philosophy of design and assembly of the vehicle. So that is something which the ISRO probably would be looking at, and this is an IP which they probably would keep close to their chest.
Sir, I have one more thing. I think what he meant is that when a human is doing a vertically ascend mission,
Uh-huh.
there is a small constraint. I mean, human cannot ascend very quickly. There is some
So that is
constraint to our
okay.
body.
No, no, that point is slightly different. See, that point you can look at it from the fighter pilots. They are also trained to take reasonably high levels of G's, right? In fact,
Yes.
humans, once they go into space, they are likely to worry more about the microgravity situation, apart from the initial launch part. So, initial launch part, they can definitely take. So, I mean,
So
typically, if you
depending
look at
on
the
that,
G
whether
values,
there
which
is
are
a
not very large, I mean, at the launch and other kind of things. See, the issue will come up is that whether the structure can withstand large G's, and the design will get. See, humans will be also trained to take whatever the G's that is necessary to achieve a mission. See, ultimately, if you have to achieve an acceleration which will take you to a particular slot in the orbit, then obviously that G would be part of your trajectory design. So the main thing would then happen is that the trajectory design would be not only driven by the vehicle configuration, but the human endurance and those kind of issues which will come up. So it's going to become a lot more complex problem in design. Whether it can be broken down in a simple term in terms of the change in ISP or propellant or change in structural design, it is very difficult to say.
Sir, I think that's what he meant because only that we are dealing with in this course.
Correct, correct.
So he wanted to see how the parameters which we are using in this course
Uh-huh.
are changing for that particular flight.
So the only maybe additional response that I can give from
Hmm,
the course perspective is
hmm,
that when we are designing a trajectory here, there is one aspect that we have not taken into account in the design is the time of flight. See, the one thing which we have not explicitly addressed, the time essentially is something which comes out naturally as a consequence of the mission, that it
hmm.
will take so long to complete the mission. For us, achieving the terminal parameters is what is the requirement. But when the humans are there, when the other considerations come into the picture, there could also be a time criticality that may have to be brought in into the design process, and there could be changes in the way we are currently such say, configuring the trajectory and the design. So there's a possibility. So this is the only point that I thought I will also make a mention, probably to give him a better perspective to Mr. Sampath.
Sampath, yeah.
Yeah.
So we have one last question from the offline form.
Okay.
So that is from Mr. Prabhat.
Uh-huh.
So he asks, Sir, assignment questions are very difficult. I'm not able to solve these questions. Even after reading many number of times your notes, I'm
Uh-huh.
facing problems to solve assignment question.
Uh-huh.
Please, sir, provide me guidance how we solve questions.
So I would make a suggestion that Mr. Prabhat can drop those queries in the NPTEL boxes where there a lot of queries are raised. They will automatically be directed to TAs, and if the and TAs then can probably provide some kind of hints and some kind of additional information which will help you to understand the solution procedure and help you to solve the problem. So suppose if there is some particular topic that you have not understood correctly and because of which you are unable to solve a typical problem, they can give you a perspective on the problem as to how the problem should be analyzed. Once you get the correct analysis of the problem, the solution would then be kind of follow the same strategy. Would that kind of address the concern that he has?
Yeah, I think so. Yes.
Mhm. So what he can do,
Uh,
and maybe that is where Sandeep can also kind of enable this particular, saying that if they have a specific issues and they are finding it difficult to solve, and if they
mhm,
want a kind of one-to-one tutorial kind of a session, see something like a tutorial
mhm,
session, where they may want a kind of a, some kind of ideas about how, what are the steps, why a particular
mhm,
step is being taken, and things like that.
mhm,
So, but then that's the purview of the NPTEL. So probably NPTEL can enable this with the help of the TAs.
mhm.
Yeah. Sandeep, I think
So
you can look at that. Yeah.
so that's all from the offline questions,
Is there
and
anything
also
left in chat box that we should address?
no, sir. Like even in
No.
chat box, I think we have addressed
Okay.
all.
Yeah. So then I think we will have come to almost
So
the end of the session. So we can
yeah,
close today's session by saying bye to all those who have joined this YouTube live session, and hope that they find this to be a fulfilling learning experience when the whole thing ends. I think somewhere in so all the lectures are not yet ended, right?
no, sir. It's not it. It's going
I
on.
think I think it should be maybe another 2 weeks, 2 to 3 weeks. I think, right?
Yeah, most probably.
Somewhere around I think
Mm,
12 to 15th April that the last lecture would get over.
mm,
So let's. So I wish all those participants all the best for the remaining part as well as the exams. And anytime they have anything, if they approach through NPTEL any other queries, even after the course is over, we'll be happy to address. So thank you and bye to all of you.
thank you. Thank you,
Okay.
everyone.
Bye, Sandeep. Bye. Bye.
Bye, sir.